Good afternoon, everyone. My name is Sharma Kolluri. First of all, I want to thank the organizers of WES for inviting me. I'm very honored, inspired. And also, I'm excited to be in this panel with this all top panelists. Storage is such an interesting subject, very near and dear to my heart. So we're going to shift gears. We've been hearing about a lot of storage projects. I'm going to talk about how to plan for storage or transmission applications of storage. That's the subject. I'm from electric utility known as Entergy in southern part of the United States. We have about 25,000 megawatts of load and 40,000 megawatt of generation. And recently, Entergy decided they're going to retire about 8,000 to 10,000 megawatts of old legacy units. We are under a lot of pressure from the regulators to replace it with renewable energy, storage, solar. We don't have wind, but solar and storage. The question is how you go about doing this, And so today we have come with a process, and I'm going to talk about the process, how to analyze, how to recommend storage, and how to justify storage, okay? This is some of the storage application. Mr. Ganesh has talked about it, I'm going to quickly cover this. One is arbitrage, buy low, sell high. By the way, this slide I took from my EEE magazine. Second is line congestion. I think someone has to seriously look into it, We have been looking into it, how to eliminate line congestion, when especially you have a heavy loaded corridor and what can you do about it. The most important is equipment capacity. When I say equipment capacity, it's like peak shaving on lines, on transformers. Great application, I'm going to talk about it, okay. Frequency regulation already covered, spinning reserves, a lot of people have talked about it. And one more new application I'm going to talk about is stability, how to improve stability using storage. So this is the methodology or a process, very simple, although there is 6 phases to it. I'm going to cover 3 phases: screening phase, siting phase, and techno-economic study phase, okay? As a screening phase, that's the first phase, basically you have a large system. How do you decide where am I going to put a battery? So you have your planning studies, you go to them, you find the best application of transmission where storage could have a potential, So basically that's the first thing you do is, hey, which planning project can I use storage there, and that's what the first thing you do. Then you basically come up with size of the storage and application of the storage, and basically rank. I'm going to show you one of the ranking process. Then, of course, the next phase is siting and sizing, pretty much coming with megawatt and megawatt hours. That's the next step. And finally, the economic studies, which is very complex because you bring all this ancillary service into picture, you levelize the cost, you come up with a net present value. So you need to have a very special tools, to perform these studies. So this is the application of screening study, very important. On the left side shows the project. On the right second column shows the storage application. And then, of course, the conventional solution and cost of the conventional solution. And finally, cost of the storage and size of the storage. Let's take example for location E. This is a transmission deferral example. The traditional plan is to build a 69 kV line, okay? So instead of building a line, if I add a storage, it will be a 5 megawatt, 9 megawatt hour storage, approximately, okay? The cost of the traditional solution is $33 million. And if you see the cost of the storage, approximately high level, is $22 million. So it's not a brainer that hey, storage is a better option here than a transmission line. So this is one project we're going to pursue. Second example is location A, backup on radial. So if you have radial line, you trip the line, the load is hanging by itself, you can add storage. But one traditional option is to build a 161 kV line, but you can add a storage, but storage is very, very expensive because the load is very large, okay? So this is how we screen the projects. We rank the project, we select the critical projects and move on to the next stage, which is the design stage. So this is one of the storage applications I'm talking about, transmission line deferral or non-wired solution. Basically, so in the top slide, let's say contingency one, that this is a 69 kV line. So when you lose a transformer, which is shown by a cross, you overload the line on the top. Okay, the overload is not very much, but it's only 3 or 4%. Similarly, when you lose the top line, you overload the bottom line. Okay, I don't know about you here, but US, the compliance says you cannot overload lines even by 1%. You have to have a project. Okay, so that's why we cannot live with it. We have to have something. So the solution is to build a line, okay, from A to B, which is, of course, expensive. You have to go through a regulatory process, but it can be done over 2 or 3 years, okay? So we said, okay, instead of building a line, since the overload is very small, why don't we look at storage? So we started looking at storage at station B and C, both on the T side and also on the D side, okay? So we did total evaluation here. So once we evaluated that, the next thing is how do you come with a megawatt and megawatt hour considerations. So we get a profile for over 1 year, 18760, okay? So you have the line profile based on the historical data, based on SCADA, and the red line shows the rating of the line. So pretty much you get a feel how much megawatts I need in the worst case condition. In this case, we came up with 2 megawatts. We said 2 megawatts will solve the problem, okay? The next thing is, how many hours do I need this? And pretty much we said, okay, we need a 5.4 megawatt hour battery to address it. So that was the starting point, 2 megawatts, 5.4 megawatt hour battery. However, all depends upon how you rate the line. Are you addressing the 100% rating or you want to bring it to 95%? So we wanted to go a step further and so that the battery would last longer. So we said we'll operate it to 2.4 megawatts. Similarly with energy, we operated it to 9 megawatt hours to get more cushion and maybe to provide more services. So this is how we came with the size of the battery. Then, of course, we definitely considered other services, what values can be provided, again, arbitrage, frequency, frequency regulation, and real-time energy settlement, And pretty much what I wanted to bring out here is, again, you can see the profile of the line loading, the line rating, and the curve on the bottom right shows when the battery can provide power and when it cannot provide. The green star shows, hey, battery cannot provide, it's almost at its limit. The red star shows, yes, battery has enough power to be provided to the system. So basically, the table on the left bottom shows that the revenues from the battery for ancillary services, if we go with 2.4 megawatt battery, was about $230,000. Now you come and say, hey, I want to increase my revenues, then you have to double the size of the battery from 2.4 to 4.8. Again, it's the cost value. So we found that increasing the megawatt gives you more value versus increase the energy, which is the vertical scale down. You can see from 9 hour, if I go to 12-hour battery, I barely gain anything, 237 versus 230 million, So that's what we found, is megawatt is more important sometimes than energy. And finally, this is the cost-benefit analysis we do. This is a very extensive analysis. It shows on the left the project, the base case is the traditional value, $34 million. Then we have a cost of storage, which is about $4.6 million, cost of land, and some of the benefits, arbitrage benefit, frequency benefits, and then we calculate the net present value. So net present value for a traditional solution is over a 10-year period was $34.6 million, okay? And if you see the battery cost, total, which is cost versus the revenues, it only is $4 million, So it's no brainer that by building a battery, I'm saving almost $30 million for the customer, okay? So this is how you analyze and you evaluate, but you need right tools to do this, okay? And it's very challenging. Now I'm going to move to a different subject, which is stability, and I quickly cover this. So here, A and B stations, we have a very critical load, very critical customer. So, and we have a generator on the left, about 350 megawatts of 2 units. So what happens when we lose the lines from A and B? The units are becoming unstable, and we cannot serve the load. The question is, how can I serve this load? How can we prevent it from tripping? So what we have come with a strategy is that when we lose 2 lines, we trip one of the generators, and then we add a battery on the station F, 10 megawatt battery. So what battery does is pretty much it keeps the speed or frequency stable, okay? So on the right, if you see the curve, the red curve actually is frequency versus time. No battery, frequency, the speed is going over 3,800 RPM, and you're going to trip the unit. But when you add a battery, during the disturbance, the generator is supplying the battery, and the frequency drops, and you put the system stable, So this is one way to apply the battery, and we're seriously considering this part also for stability. There's again some plots showing how the battery behaves during the disturbance, how charging and discharging goes on. The left plot shows the power and Q of the battery. Right side, it shows the voltage. Battery could be operated under the frequency mode or a voltage mode. It cannot be operated in both the modes. So in summary, I would say be careful when you plan a battery, It offers several applications. Carefully evaluate your applications. Do a benefit cost analysis on the battery, optimize the size. And finally, life cycle management is very important, Look over the life and make sure safety is there, So that's all I have to say, Thank you very much.
Thank you very much, Mr. Sharma. This is really interesting to see all the work which is happening at Entergy, and since I started my career looking at energy storage in US and having participated in number of meetings with utility officials, it's really nice to see the work which you are doing. Hopefully that can also advance storage on the transmission side in US. Thank you.